Well, first of all, I want to thank my co-authors, Meiji Nguyen and Rob DeRosa. They did outstanding work on this project, which was very difficult, actually, to determine the orbit of 106-906b. But as an introductory slide, I wanted to show you a diagram showing the known extrasolar planets as a function of separation and the mass of the extrasolar planet. And the talk today is about the directly imaged exoplanets, which are up here. Due to the limitations of technology, we are currently sensitive to young luminous giant planets at wide separations. And of course, this is going to improve in the future as we build new telescopes with new technologies, and eventually we'll be able to image reflected light planets. But the nice thing about the planets that we're imaging up here is that they're much younger than the planets that Angelos and others are studying. So direct imaging gives us this opportunity to probe the early evolution of a planetary system. Here's just a sketch from 1 million years to a gigayear. And with direct imaging, we're looking at the circumstellar disks where exoplanets are born. And then in the 10 to 100 million year age range, we can sort of see different evolutionary pathways, which I generally split into low eccentricity pathways here on the top and high eccentricities here on the bottom. And the question is, what determines which pathway a planetary system will take? Do you have early dynamical evolution that is the most important when the star is still in its birth cluster? Or do you have other evolutionary pathways that govern the final architecture, such as planet-planet scattering, which I call here late upheavals? So to get an empirical grasp of what's going on, we've been studying the 106-906 system down here, which has age 15 million years, and it appears to be highly perturbed and dynamically hot. So in 2015, this is what we knew about the system. It's actually surrounding a spectroscopic binary, 2 F5 main sequence stars, distance of 103 parsec. And with before we imaged the debris disk, we knew it had a distant giant planet, 106-906b, with 11 Jupiter masses. And the separation is astonishing, 737 AU. Using the Gemini Planet Imager and the Hubble Space Telescope and a separate group using SPHERE, we all imaged the debris disk, and we were rather surprised to find that the debris disk is misaligned with the planet, or the planet is misaligned with the disk. If you look up close into the ground-based adaptive optics image here, you can see that there's a central hole in the disk, and this is thought to be a central planetary system, and this radius here is roughly 50 astronomical units. But on a much wider scale here of 500 AU, you see a highly distorted disk and a misaligned planet. And the question is, what are we looking at here? How did the planet end up at that large distance if it formed in a circumstellar disk? Or did it actually form in situ by a gravitational instability? Or could 106-906b have been a planet captured from another star? So these were all mysteries. And one of the other questions is, does the planet account for the disk asymmetries? Is it 106-906b the dominant perturbing force that causes the highly asymmetric structure of the disk? And this was investigated theoretically, and of course, you can perturb a disk if you assume certain orbital elements for 106-906b. And the most detailed model was actually proposed by Rodet et al., where they actually tried to explain how 106-906b ended up in its distant eccentric orbit. And here is the model that they produced. First, you have the formation of the giant planet, 106-906b, a few AU from the central binary. And this planet migrates inward due to interactions with the circumstellar disk. And the planet reaches an unstable resonance which then rapidly changes the orbital elements of the planet so that it becomes highly eccentric, semi-major axis increases, inclination may be perturbed, and eventually the planet should be kicked out of the system. To prevent that, you have to raise the periastron distance away from the instability zone. And this is accomplished by a stellar flyby. At least this is what the model proposes. So we were interested in testing two aspects of this model empirically. First, to search for these stellar flybys, and then to actually look to see if we could determine the orbital elements of 106906b. Which at this stage is completely unknown. All we know is the projected separation of the planet from the star. So in our first paper with Rob DeRosa, we actually used the Gaia DR2 to trace back the motions of the 461 SCO-SEN stars. So 106906b is in the SCO-SEN OB association. And we wanted to test for the stellar flybys. And by using the Gaia catalog and radial velocities from the literature, we calculated the closest approach times and distances. And we did in fact find a close approach of these two stars, which are themselves a binary. And this closest approach happened 2 to 3 million years ago, and the closest approach distance is roughly 0.7 parsec. So the next question is, what is the orbit of 106906b? And here is the problem. A planet on a circular orbit at a separation of 737 AU has a period of 12,000 years. So this is a rather difficult problem. All the other extrasolar planets where we have determined orbits through direct imaging have orbital periods of roughly 10 to 100 years. And here we're dealing with 12,000 years. Nevertheless, this corresponds to a velocity of 1.8 kilometers per second, which at 103 parsec corresponds to 37 milliarc seconds in 10 years. So could this be feasible using the Hubble Space Telescope? And here on the lower right, I have a chart of all the Hubble Space Telescope observations starting in 2004, when it was observed with the advanced camera for surveys chronographically. And this had very fine sampling of 25 milliarc seconds per pixel, which makes this astrometry problem seem tangible, except that the camera electronics failed, and the subsequent data sets are with the WIPC3 camera that Angelos just talked about, which has 128 milliarc second pixels, and the STIS camera, which has 51 milliarc second pixels. So the problem did indeed look difficult, but we thought we would give it a shot. But these large pixels is not the only problem. The major problem is that the star 106906 is almost never in our images. It's blocked by a coronagraph or it's saturated. So here is the image from 2004, and the star is behind an occulting wedge, and here's the scale here, 5 arc seconds. So even though we would like to do relative astrometry with respect to the planet shown here, the central star position is very hard to determine. And the same goes for the STIS data. Here's the planet, and here's the star. And so the same is true with WIPC3 data, where there is no chronographic element. This is just direct imaging where the star is saturated. And here's a scale bar again of 5 arc seconds, and here's the planet. So the solution was to use the Gaia catalog to create an astrometric reference frame within each image. So every star here that is surrounded by a square is in the Gaia catalog. The planet B is not detected by Gaia, but 106906, the star, is detected. So we could essentially find the position of 106906 at each epoch using our Gaia sources. So we have a precise determination of the stellar position, and then we could get the relative astrometry with respect to the planet B. So our first result was that we actually discovered that the STIS camera has an error in its orientation header keyword. If you look at this, here's time here, and this is the error in the STIS camera true north orientation, or the position angle, which amounts to 0.1 degree at the current epoch. We also determined that it had a slight error in the plate scale. The other cameras were confirmed to have good parameters for orientation and plate scale. But the scientific result is that we detected the orbital motion. The two most constraining points were the ACS data point from 2004 and the STIS data from 2017. We found roughly 32 milliarcseconds eastward motion, and this corresponds to a projected velocity of 1.2 kilometers per second, which is half the escape velocity. But notice that we do not have the radial velocity of the planet. That hasn't been measured yet. But at face value, it looks like the planet is bound. It's not on a radial trajectory, and it doesn't have sky plane velocity that exceeds the escape velocity. We then used this astrometry to fit orbits to the planet, and here are the parameters on the right. The period is 15,000 years, semi-major axis of about 850 AU, and the periastron distance of 510 AU. So this means that the periastron is roughly out here. So the planet's periastron, we believe currently, is outside, just outside the debris disk. And also we find a high mutual inclination of roughly 40 degrees and a relatively high eccentricity of 0.4. And this is a comparison to one of the prior theoretical models, which in their models, they inserted 700 AU for semi-major axis, 0.7 for eccentricity, and a mutual inclination of 5. So now we have an estimate of the true orbital elements, and what remains to be done in the future is to actually rerun these models. This hasn't been done yet. So now we can say that 106.906b is very likely bound to the binary, which we didn't know before. It has indeed a very large semi-major axis, and its periapse appears detached from the planetary region. And this looks like the scattered Kuiper belt objects, the detached Kuiper belt objects like Sedna in our own solar system. The plot on the right actually plots the orbits of Sedna and the other detached objects, as well as the hypothetical planet 9. So here's a nicer plot that shows the dynamical populations of our solar system, semi-major axis on the x-axis and eccentricity. And you see the resonant populations of low eccentricity objects that comprise the classical Kuiper belt. You have the scattered disk. And then out here on the right, you have the detached Kuiper belt objects, which have high eccentricities, large semi-major axes, and they never interact with Neptune. Their semi-major axes, their periastra are greater than 30 AU. And if we plot 106.906b, that's what we determined for its orbital elements right there, just like our detached Kuiper belt objects, except with a somewhat lower eccentricity than Sedna. However, since we, okay. Yeah, I have a minute maybe.
Yeah, okay.
So since 106.906b is thought to be perturbing the degree disk, this invites a comparison to our hypothetical planet 9 in our solar system, which is thought to perturb the detached Kuiper belt objects. Here on the right are the plots of the detached Kuiper belt objects, which have a clustering of their arguments of perihelion such that it's been proposed a 10 Earth mass planet, planet 9, is shaping, is is shepherding these detached Kuiper belt objects. And so indeed, if you compare our orbital elements to that of Planet 9 and even the detached Kuiper belt objects, they're rather similar. The big difference is 106906b is known to exist and is an 11 Jupiter mass planet, whereas Planet 9 is hypothetical and a much lower mass object. Okay, I think I'm out of time. I did want to emphasize that this type of work will help us understand how these distant planets form, either Planet 9 or 106906b. It's still possible that they formed through gravitational instability. This has to be determined by future work. Our current hypothesis is that they formed in a disk and were scattered outwards and later stabilized by passing stars. And it's certainly possible that some of these objects are captured in the early cluster environment. Okay, so in summary, we've been looking at this system closely. We found the flybys in our 2019 paper, and in our 2021 paper, we actually made the first measurement of the planet's orbital elements. Okay, thank you.
Thank you, Paul. Any questions? Paul? Maybe we have a minute or so. Yes. Yes, please. I think you can unmute yourself. Dimitri. Dimitris Veras, can you hear me?
Now I can hear you. Yes. Okay. For a while I couldn't unmute.
Okay.
Well, hi, Paul. That's a really exciting system. I was just wondering about the stellar birth cluster environment in terms of explaining the not just the orbit of the planet, but also some of the features in the disk. Because due to multiple I imagine the system is quite young because you can directly image the planet. And so it probably hasn't left the birth cluster all that long ago. And so maybe multiple flybys could have shaped the orbit of the planet, but that could have also perhaps created at least this tilt that you see in the disk, if not any other additional features. I'm not sure if you could pick out any other additional features or cavities in the disk, but I was just wondering if that's a viable possibility.
Yeah, so all of this remains to be explored further. So these two flyby stars here, these are F stars, and what we're missing from the Gaia catalog are the most numerous objects in the cluster, which are the M dwarfs. So it's quite possible, for the sake of time, I didn't have a chance to explain that this flyby is rather too far away from 106906b. It's the closest stellar flyby, but it probably did not shape the orbit of the planet. It's more likely that another star has yet to be discovered, probably an M dwarf that had a much closer flyby than this. To have a significant dynamical effect on the planetary system, it would be useful, it's reasonable to have a flyby that is 10 to 100 times closer than what we see here. So 0.07 parsec would work better than 0.7.
Okay, thank you.
Angele, I believe you have a short one.
Okay, I can talk now. Thank you, Paul, for the presentation. It was an excellent one. Very quick question. When you did the Gaia, when you use the Gaia coordinates for the obscured star,
Mm-hmm.
These observations are in different epochs. So are the proper motions playing any role in this estimation?
So yes, I mean, Gaia, I'm sorry, not sure what the question is. Obviously, we do have the proper motions and parallaxes of these objects. What was your question exactly?
So the star itself should have a proper motion, right?
That's right. We do. 10696b has a proper motion. It's a common proper motion to 10696b. So these two stars, the planet and the star, have the same proper motion. That's why it's confirmed that 16906b is physically connected to the star. And we have all the proper motions of all these objects from the Gaia catalog. Yeah. And not only that, we tried to determine if we could find a common parallax between B and 106.906. But the error bars don't give you an answer, actually. We don't have an answer for that yet.